Hello, ERA users. Today I want to talk to you about a number of technical issues that you should be aware of when using ERA4 and some of the new features and capabilities that it has. The issues generally revolve around downhole density, how it's input, issues to be aware of when we're collecting data from the field, and also how to manipulate the software to produce correct results for different operations. And where this comes up most often is when we're either tripping or backreaming out of the hole. And to illustrate the point that I want to make, I've got an example here from the Danish sector of the North Sea. And the well's not particularly high angle, and it's not particularly deep. We're looking at about 7,000 foot TVD, and the operators drilled 12 and a quarter by 13 and a half inch under-reamed hole. They're using 13.8 pound per gallon water-based mud, and that density was measured at 120 degrees Fahrenheit. And you can see from our surface density versus temperature conversion chart that at 120 degrees Fahrenheit, that 13.8 pound per gallon mud weighs considerably more, up to 14.1 pound per gallon at 60 degrees Fahrenheit, or considerably less at 200 degrees Fahrenheit, 13.4 pound per gallon. But the point of this exercise is really to show you what happens with the temperature downhole when we do different operations. Now we believe that we have a fairly well calibrated temperature simulation. You can see in gold the geothermal temperature. It's cold in the water, not very deep water, and then it gets progressively warmer below mudline. Bottom hole temperature is only 170 degrees Fahrenheit, so this isn't a particularly hot well. Now I have an MWD trace of what the temperature was at the MWD as this interval was being drilled from the intermediate casing to TD. And you can see at TD we end up with an MWD temperature of around 160 degrees Fahrenheit. Now if I overlay a snapshot of what the temperature profile is from the MWD all the way back to surface, you can see that the majority of the well is close to 160 degrees Fahrenheit, terminating at surface at somewhere around 135 degrees Fahrenheit. So most of the well is pretty warm, certainly warm compared to the static geothermal gradient shown in gold. Now, if we were to simulate what the annular temperature snapshot would look like during the backreaming process, the wellbore temperature would be considerably cooler, from 160 degrees while drilling down to 130 degrees if we were to backream at TD with the parameters that were being used on this operation. Now, this particular operation, it reduced parameters from 1200 GPM and 150 RPM down to 980 GPM and 60 RPM. And that's an important change because it means that we have significantly less hydraulic heat and significantly less torsional heat that is driving up the over wellbore temperature. And that's what's reflected in the simulation. Now, because ERA is a steady state temperature model, we do not capture how much heat is stored in the formation as we go from several days of drilling and putting in a tremendous amount of heat by comparison at this 160 degree Fahrenheit line compared to the backreaming operation, which if we were truly at steady state conditions would be represented by this 130 degree Fahrenheit line. Now, as we backream, they backreamed from TD back to about 4,500 feet measured depth, and the red data represents what was recorded by the MWD tool as they were backreaming. And as you can see, the actual data doesn't follow the brown curve, nor does it follow the pink curve. It's somewhere in between, again, because this is a steady state model and not a transient model, so we kind of have to read between the lines of what the wellbore temperature will be during that operation. Now, if I was to simulate what the temperature snapshot would look like if I cease backreaming and start to pull out of the hole, the backreaming temperature profile, when I get to the previous casing shoe at around 4,500 feet, should follow somewhere around this 95 degree Fahrenheit line. And as you can see, when they tripped out of the hole on elevators, the actual MWD recorded temp was more in line with this green profile. Now, why this is important is because it gives us some insight into how we should use the steady state model. Clearly, the static temperature is not correct, nor is the pink temperature line, nor is our brown backreaming curve. However, the degrees of wrongness is significantly less if we were to assume that the wellbore temperature followed the pink snapshot line purely from an equivalent static density standpoint. The most conservative thing to assume while we're calculating Swab or ESD is that the wellbore is quite warm. And you can see the pink curve is the warmest assumption that we could make if we're trying to simplify things and just use the steady state engine. rather than the brown or the gold dotted curve. So what that means is when we go to simulate our trip out or even backreaming out, what we ought to do is be conservative and assume that the wellbore temperature is no different than it was when we were drilling at TD. And therefore, we've introduced that option in ERA version 4.2. You can select what the temperature profile was when you finished drilling at TD as one of your options when you go to trip out or go to trip in. So I just want to point that out. We'll come back and look at that in the software in a minute. The consequence of this temperature profile when we look at static conditions versus the temperature profile when drilling at TD, here we've got our static temperature profile. We've got our swab load sensitivity to trip speed. So 150 feet per minute is my base case trip speed. And I'm looking at sensitivity on 50 foot per minute increments. So we're tripping as slowly as 50 feet per minute or as quickly as 250 feet per minute. We're trying to stay above this gold or yellow shaded area, which is the collapse gradient. The green line is my surface mud weight, and the pink curve is my equivalent static density. This is a snapshot plot, so this shows me my ESD downhole all the way back to surface. You can see that the fluid gets more dense as I move shallower into the colder region. Now, this simulation on the right is all assuming a static temperature profile in the well. If I switch it to the drill at TD temperature profile, which is represented by this green curve, it's no different than the pink dashed curve we saw in the previous slide. You notice that the ESD is now lower than my surface mud weight. My ESD is now 13.7 pound per gallon at TD, and it's not a lot higher than that even at surface, simply because the wellbore is so much warmer when we make that drilling at TD temperature simulation. And you'll notice what that means is with a lower ESD, my swab load now drops below the collapse gradient. Very different results if I was to assume static temperature profile versus drill at TD temperature profile. That is the temperature profile that we should assume whenever we go to trip on elevators to retain conservatism, both from a well control and wellbore stability standpoint. Two other issues to be aware of as long as we're on the subject of density. One of them is how mud weight is recorded. A pressurized mud balance needs to be used at the rig site on all wells. And this is because any air or gas that's entrained in the mud system, particularly an issue with oil-based mud, will make the mud appear lighter at surface than it actually is. So if the mud engineer is asked to maintain a certain density and he's not using a pressurized scale, he'll have to add substantially more barite to compensate for these air bubbles that are entrained in the system. If we put just a little bit of pressure on the mud and compress the air bubbles, the density will be much more correct and much more reflective of what it looks like immediately below the bell nipple in our well as we start to pressurize that fluid column. If we don't do that, if we don't use a pressurized mud scale, then what that will result in is a higher measured equivalent static density and a higher measured equivalent circulating density than what our hydraulics model will predict. Because in fact, we're using denser mud than what is reported. So absolutely critical, have to use a pressurized mud balance. Second issue is density normalization. On occasion, this is rare, but on occasion, some operations will normalize their measured mud weight back to a certain standard condition, a certain standard pressure, certain standard temperature. Now, most projects, this is not an issue for most folks, but on most projects, the mud weight that is reported is reported very closely to the flow line temperature. And however much cooling takes place between when the sample is caught and when the density is actually read, there's a small difference, but it's fairly close to flow line temperature. So what that means is when we're maintaining a mud weight, if the mud engineer is tasked with maintaining, let's say, for example, 10 pound per gallon mud, as the well is being drilled from our surface or intermediate casing down to TD, and the flow line temperature is steadily increasing, if we maintain the same mud weight, what that means is the mud is actually getting heavier. We have to add barite in order to maintain the same measured density at increasingly higher and higher and higher temperatures, like this graph illustrates. If I was to measure mud of 10 pound per gallon at 100 degrees Fahrenheit, if I wanted to maintain 10 pounds per gallon, but I'm way over here at 170 degrees, if I had not added any barite to the mud, what that 10 pound per gallon mud at 100 degrees Fahrenheit would actually weigh is about 9.7 heavy. So a substantial decrease in the mud weight. Of course, the mud engineer isn't going to report 9.7 pound per gallon when he's been tasked with maintaining 10 pound per gallon mud. So two options: either lie about the mud weight or increase or add barite in order to maintain that 10 pound per gallon at steadily increasing flow line temperature. So that is the typical procedure that we use. Whether we're aware of it or not, the mud density is effectively increasing as we drill. Now, once we get to TD and we stop drilling and the pumps are turned off and the wellbore starts to cool, and certainly even our flow line temperature will begin to cool, the density that we measure at surface, if I actually had 10 pound per gallon at 170 degrees, I would read 3 points higher mud weight at 100 degrees Fahrenheit, because it happens in reverse as well. When the mud cools, it gets heavier. And that's another good check to see if our mud engineers are being honest, because if the mud density is truly the same, then once we measure it at a lower temperature, it will be recorded heavier. Now, as I mentioned, some HPHT projects correct their measured mud density back to some common standard, which causes some really weird things to happen. So if you ever see this, and this is a great example from an HPHT project in Norway. They're drilling 17.5-inch hole. It's not terribly hot at TD. By the time they get to TD, it's 225 degrees Fahrenheit, so not super hot. But what they're doing is they're normalizing their measured mud weights back to 20 degrees Celsius, which is 68 degrees Fahrenheit. And we weren't aware of that when we were first drilling the well. You can see that we have a good temperature simulation match. The brown circles are our MWD temperature. Red is the curves are simulated. And then, of course, we have simulated flow line versus actual flow line. Not a perfect match, but pretty darn close. On the right, you'll notice that we've got a discrepancy between our calculated ESD in pink and our measured ESD in these little black circles. Now, our surface mud weight was reported in this interval of the well to be just a little over 12.3 pound per gallon. But you'll notice that the ESD is steadily decreasing, decreasing, decreasing. Now, we're running this simulation assuming that the temperature that was reported when the density of the mud was weighed is correct. But in fact, what the mud company was doing was adjusting the weight that they actually measured back to 60 degrees Fahrenheit. What would this mud have weighed if it was at 68 degrees Fahrenheit? Well, if it was 68 degrees Fahrenheit, this is the density that we would await, this black vertical line. Well, when we find out that they're doing that and we run the simulation correcting for this normalization, you'll notice that the calculated ESD now matches the measured ESD. So it's very important to know whether or not we're reporting actual measured mud weight temperatures or we're normalizing to a certain standard condition. Personally, I don't like this operational technique or this approach. I think it's too confusing, especially since for years and years we have used a very different approach, and that is to report the mud weight at or close to the flow line temperature. When we're in planning mode and we're using ERA, what we want to be doing is telling the system that the mud weight that I specify, we want to specify that mud weight not at the library values. Notice in ERA, most of the library values are 75 degrees Fahrenheit, but rather what is the flow line temperature at TD. And we can, of course, run a temperature simulation and find out approximately what the flow line temperature is at TD. On this well, if I just ran this ECD simulation at 75 degrees Fahrenheit, if I told it I had 9 pound per gallon mud at 75 degrees Fahrenheit, the pink curve represents the ESD driller's view as the well's drilled, and then of course blue over here is the ECD. But if I specify that I'm using 9 pound per gallon mud at 135 degrees Fahrenheit, which is representative of what I'll have at TD, then you'll notice that my ESD increases from 9 pound per gallon to 9.2, and my ECD increases from about 9.3 to almost 9.5 pound per gallon. This is more representative of what we'll actually see when we drill this well, when we're at TD, of course. So those are a couple of very important points to keep in mind. The ways in which density can be wrong and the ways in which we can use our simulation incorrectly. Now I'm going to show you another quick example within ERA itself. And I've got a simulation loaded here where we're drilling a very long, shallow TVD well. I've got a valid thermal simulation. You can see in blue is my modeled flow line, red is my modeled MWD temperature. This was in drilling mode. I had good agreement between my measured ESD and my modeled ESD, and of course my measured ECD and my modeled ECD. On this project, when we went to trip out, we backreamed out. And you'll notice in all tripping sub-operations within ERA, we now have three options. We have static conditions, so we assume that the wellbore temperature is static, even if we are circulating. Then we have circulating, which is appropriate for backreaming or pumping out operations. And then we have drill at TD, where we use whatever the temperature profile was when we were drilling at TD. For this well, you'll notice that the ECD, while we were backreaming out, modeled versus measured, agrees really well whether we use the drill at TD temperature or the circulating temperature. And that's just simply because there's not much difference in this particular example between those two simulations. Teal here is our simulated MWD temperature, and then of course over here we have our simulated versus actual ECD. Both agree quite well. Static would be incorrect. You'll notice that the ESD is a couple of points higher if we assume a static wellbore temperature because it's so much cooler than the circulating wellbore temperature or the drill at TD wellbore temperature. Both of those are quite a bit hotter. On this well, there's not much material difference. We're backreaming all the way out of the hole purely to overcome swab in the first place. But if I was to show you an example of where we're tripping out on elevators, so same well, but now we're just going to pretend we're tripping on elevators. Notice our static temperature profile. We've got our static swab load. So here we've got a 9.4 pound per gallon surface mud weight. At static temperature conditions, that means that the ESD is 9.6 pounds per gallon because I've got a fairly cool wellbore, and I measured my 9.4 pound per gallon at a very high well, not a very high temperature, but at 95 degrees Fahrenheit. And you can see that most of my well is not 95 degrees Fahrenheit. It's less than 95 degrees Fahrenheit. That's why my ESD is higher. And then you can see my ECD, my swab loads at different trip speeds. Now try to ignore the fact that I'm dropping below collapse. That's my green and my red, but let's just focus on pore pressure here. I believe I have a 8.4 pound per gallon pore pressure. And the way I've run the simulation, that would seem to suggest that if all I'm trying to do is avoid dropping below pore pressure, I could do so by just pulling slowly, as long as I don't pull any faster than this green curve, which is about 30 feet per minute. As long as I don't pull faster than 30 feet per minute, I won't drop below pore pressure. However, remember, I pumped a lot of heat into this wellbore when I drilled it, and so I should be using the drill at TD temp, and that will be the default setting. For those of you that have downloaded ERA 4.2, the default will be drill at TD. And you'll notice now with the drill at TD temp, that 30 feet per minute trip speed will swab below pore pressure because my ESD now is approximately 9.4 pound per gallon rather than the 9.6 pound per gallon that I had assumed when I had a static temperature profile. I hope all of this wasn't too confusing. It is a complicated subject. It's something that we hadn't considered, I hadn't considered when we first rolled out the software, and some very smart people brought it to our attention. Hopefully this is a useful educational video that will prevent you from making some of the same mistakes. Please email us if you have any questions, bfoster2@kmtechnology.com.